Mass percent is mass of solute over mass of solution times 100. And mole fraction is moles of solute over total moles. No times 100, and there's no unit for that either. For mass percent, your percent should add up to 100, so you can also do mass of solvent over mass of solution, so it doesn't have to be just the solute. And for mole fraction, your solute and solvent mole fraction should add up to 1. And so again, you could have mole solvent over total moles. We'll also see mole fraction in the gas unit. Dilution is the addition of water to a concentrated solution. When you add water, the number of moles will remain the same. Molarity is equal to moles over liters. So if moles before is equal to moles after, molarity times liters is equal to molarity times liters. So when we multiply those, our moles will remain the same. It doesn't matter that if you make the concentrated 1s or 2s, as long as the concentrated is on one side and the dilute is on the other side. So for example, in this problem it says 100 or 10 milliliters of 12 molar. Those have to go on the same side. We're diluting it to a new volume of 1,000 milliliters, and it wants to know what's the new molarity. So to solve that, I just need to multiply and then divide by 1,000. And I get 0.120 molarity. Besides solving dilution problems, you also need to be able to explain the steps. This problem, make sure that you're writing small enough where you can write the steps that you would use to dilute 14 molar copper chloride to 100 milliliters of a 6 molar solution. I'm going to pause the video and calculate how much of that 14 molar copper chloride you would need to make this solution. So step 1, we would need 43 mils. And again, the 43 mils is X, which is with 14 molar. So step 1 is we would measure 43 milliliters of 14 molar copper chloride using a graduated cylinder or a burette or even a volumetric pipette. We wouldn't use a beaker or a Erlenmeyer flask. We would need to use something accurate. More accurate would be a burette or a volumetric pipette. Then, this is already a solution, so I don't need to dissolve it. I can pour it directly into the volumetric flask. In this case, I'm making 100 milliliters, so I need a 100 milliliter volumetric flask. Then the best practice would be to rinse the graduated cylinder with small amounts of DI water, pouring the rinse into the volumetric flask, making sure that I got all of the copper chloride in my volumetric flask. Then, just like with molarity, I'm going to add DI water to the volumetric flask until the final volume reaches the 100 milliliter calibration mark. And also, just like a molarity problem, I would cap and mix. So here's a visual of that. In this picture, a volumetric pipette was used to get some solution from the stock solution. Stock solution is also referred to as the concentrated solution. So the more concentrated, I measure out how much I need, and then I put it in my volumetric flask. Once I have that, then I just add some of the water till I reach the calibration mark. Notice that the concentrated solution is darker than the dilute solution. I'm going to pause the video and finish writing any of these steps down. Make sure you have these steps because you will have them on your quiz and test. To solve this one, you need to know that ethanol is C2H5OH. Go ahead and pause the video and try solving this one on your own. Restart when you're done. So there's a couple of ways you could have started. I went ahead and did mass percent first. So that's mass of solute over total mass. And my total mass is my mass of solution, or 101 grams. So solving that out, I got 0.99%. So next I calculated my molarity. So I calculated my moles of ethanol, and I saw that there was 101 milliliters of solution. So converting that to liters, I got 0.101 or 0.22 molarity when dividing those. And then the last one is mole fraction. And for my mole fraction, I had 0.022 over 0.022 plus 5.551. And mole fraction is represented with this X, which is technically chi, and that is 0.0039. So a really small mole fraction of ethanol, since very little of the solution is ethanol. Go ahead and pause the video and try solving this one. Restart when you're done. So this problem, they gave you grams, and if they give you grams, it's not dilution, and they gave you a capital M, so this should have been just a molarity problem. From the molarity video, remember that molarity is a conversion factor, so that's giving you moles per liter. So I'm going to start with the grams. Once I get moles, now I can say, well, I can have to put moles on the bottom so they cancel out, and I'm going to have liters. And according to this, 1 goes with liters and 0.014 goes with moles. And then we want the answer in liters, so we're done. Notice my grams are canceling, my moles are canceling, I'm left with liters. So 0.789 liters. Another type of question you could see is where we're going to combine two solutions, and we want to know the concentration after the two solutions are combined. In this case, no reaction has taken place. We just want to know what the concentration is after we mix them. Well, if we're mixing solutions, then we're going to dilute the two solutions. So we need to use the dilution equation. I'm trying to find the concentration of silver, and the only one that's giving me silver is silver nitrate. So originally I had 100 milliliters of silver nitrate, and I have 0.250 molarity. Notice that silver nitrate, when it breaks apart, is going to give me 1 silver and 1 nitrate. So my concentration of silver is 0.250 molarity to start with. But when I combine the two solutions, my V2 is going to be 100 milliliters plus 83.2 milliliters. So 183.2 is my final volume, and I'm trying to find the new concentration of silver. So solving that out, I get 0.136 molarity of silver ions. So this problem is the same, except now I want to know about my concentration of sodium, and I want to know about after the reaction takes place. So this one's a little bit trickier because first, sodium phosphate breaks up into 3 sodium ions and 1 phosphate. So if I have 3 sodiums, then my concentration is going to be 3 times 9.22 times 10 to the negative third, or 0.02766 molarity. That's before the reaction takes place and before I've mixed the solutions. So my initial concentration is 83.2 milliliters and 0.02766 molarity. So this is my before. Then once it reacts, my new volume is going to be 183.2, as we saw in the last problem. And I'm finding my new concentration. So solving that out, I get 0.0126 molarity of sodium. But I wanted to know after the reaction took place. So the reaction is sodium phosphate reacts with silver nitrate to produce silver phosphate and sodium nitrate. Sodium phosphate is aqueous and sodium nitrate is also aqueous, which means that both of these are going to be spectators. So my sodium is a spectator ion, which means the concentration for sodium before and after the reaction takes place is going to be the same after they're done mixing, because sodium's not reacting. It was floating around at the beginning, it's still floating around. Had this been silver though, then this problem would have been a lot more complicated, because we'd have to figure out how much of that silver went into the precipitate and if we have any more left over. If silver was a limiting reactant, then I would have none left over because it would all be in the solid precipitate. But for sodium, in this case, it didn't matter if this question said before or after, the answer still would have been the same because it's a spectator.